What we're going to do just now is we're going to look at two theorems, closely related theorems, the factor theorem and the remainder theorem. And they can be used in a variety of ways. So I'm going to try and introduce them just now. Suppose you were asked to factorise x cubed minus 3x squared plus 3x minus 1. You know how to factorise a quadratic. That should be basic. But this is significantly more difficult. Apart from anything else, we can't see any obvious factors. So we can use the factor theorem. The factor theorem says if f of a equals naught, then x minus a is a factor of f of x. While I'm at it, the remainder theorem says that if f of x is divided by x minus a, and the remainder is b, then f of a equals b. We'll come on to the remainder theorem a little bit more later on, but that's both of them stated. Now, we want to find a factor of this cubic. We're going to use the factor theorem. We're going to treat this as being f of x equals x cubed minus 3x squared plus 3x minus 1. And we're going to use some trial and error. F of naught, we can actually see straight away that it makes minus 1. More importantly, it doesn't make 0. X on its own, x minus 0 if you like, x isn't a factor of the cubic, and that's a trivial result because we could see that right at the beginning. So we'll actually get rid of that one, but it was an option. We can actually be a little bit more intelligent. This number on the end, this minus 1, that gives us a clue as to possible factors. If this had said minus 6, then we would be thinking of possible factors such as positive 1 with positive 1 with negative 6, negative 1 with positive 6, likewise for 2 and 3. We wouldn't try a factor of 4 if that was a 6 on the end. So the only sensible options to go with are 1 and negative 1. So we'll try that. Let's see what happens if we use f of 1. 1 cubed minus 3 times 1 squared plus 3 times 1, take 1. 1, take 3, plus 3, take 1. It makes 0. And so from the factor theorem, we conclude that because f of 1 equals 0, then x minus 1 is a factor. And that's a really useful piece of information, because what it means is, now that I know a factor of this cubic, I can now use algebraic long division to factorise, hopefully, the entire cubic. Perhaps I will discover that it has other linear factors. Perhaps I will discover that the quadratic that results from this can't be factorised. I don't know, but we can try. X goes into x cubed, x squared times, multiply x squared times x squared times minus 1, do a subtraction. Negative 3x squared plus x squared makes negative 2x squared, and bring this down. Okay, we've done DMSX for the first iteration. We now do it again. X into negative 2x squared makes negative 2x. Multiply gives me negative 2x squared plus 2x. If I now subtract, that gives me positive 1x, and bring the minus 1 down. X goes into x positive 1 times. Multiply 1 times x, 1 times minus 1, do a subtraction, gives me 0. Now that remainder of 0 should not surprise me. I knew about it already here, where we discovered that f of 1 made 0. The remainder of 0 corresponds to this f of 1 equals 0. That's the remainder theorem. In practice, in the very specific situation where there is no remainder and we actually have a factor. Now let's look and see what we've actually discovered. We know now that x cubed minus 3x squared plus 3x minus 1, we know that is the same thing as x minus 1 multiplied by this quadratic up here, x squared minus 2x plus 1. Can we factorize that quadratic? Yes, we can. X times x, 1 times 1, negative 1 times negative 1 makes the positive 1, but also provides me with that negative 2x. And so that cubic, which looked so complicated, is actually best written like that.